All right.
Cool.
So today we're very happy to have Ning Bao from Northeastern University giving us a talk that I'll tell you the title in a second. Please, Ning.
Okay, so today I'd like to talk to you about an exponential speedup in finding contraction maps. Or holographic entanglement entropy inequalities. So closely related to what we were just talking about, but a separate project from the one engaged here. And this is work which is completed, but is in the process of being written with my student, Joydeep Naskar, and Sergio Hernandez Planca. I will be very unhappy if it does not come out sometime this year. But I won't be so bold as to write a month. Okay, so what's the background? So entanglement entropy it quantifies how correlated one system, a subsystem, is with its purification. The reason why it matters is because entanglement is and some would say the key resource in quantum information science or quantum computing. So quantifying how much entanglement you have is very important. However, while quantifying entanglement is important, it's also very difficult. You can see why from the form of the entanglement entropy. The entanglement entropy of some density matrix rho A is equal to the negative trace of rho A log rho A, or if you like, the negative sum of lambda I log lambda I, where the lambda i's are the eigenvalues of the rho A. So if you have a 2-qubit density matrix, so a 4x4 matrix, trying to find the eigenvalues via a diagonalization procedure is not challenging. But if you have a 1,000-qubit density matrix, then trying to diagonalize a 2 to the 1,000 by 2 to the 1,000 matrix becomes very taxing. And in the limit that the number of qubits goes to infinity, calculating the entanglement entropy is impossible in general. So we have this tension where we have this thing that's very, very important to quantify, but in general, it's very difficult to quantify. So in quantum information, what do? Well, we bound it. This is what we always do in mathematical physics. If you find something and you can't compute it in general, you write down bounds of it and try to make progress in that way. So some bounds that are known that are true for all entanglement entropies are that the entanglement entropy is positive, it's subadditive, and it's strongly subadditive. The last one was proven by Lieb and Ruskay in I think 73. And their proof of it was like about 50 pages long. Where I only mentioned that detail because the proof of it is very difficult, or the original proof of it was very difficult. And you can kind of intuitively understand why it's very difficult. This inequality looks linear, but it's actually a nonlinear inequality. Because if you think about the objects that you're considering as the inequality as being the density matrices as opposed to the entropies. And that's because this is not a linear operator on the density matrices. So the nonlinearity of the definition of the entanglement entropy is inherited in terms of the inequalities that you can try to prove on it. And indeed, maybe relatedly, no further inequalities of this form have been found for all quantum states since Strong's additivity. So this one is the state of the art in full quantum information science. And it was discovered now 50 years ago. So if that was the only thing that I wanted to talk about, this would be a very short and very boring talk. But like, we have some extra things that allow us to make more progress. If we just concern ourselves with CFT, then Cardi and Calabrese give us in 1D CFT or 2D CFT, I guess, the so-called Cardi-Calabrese entanglement entropy formula, the Cardi entanglement entropy formula, which says that the entanglement entropy of some region rho A that's defined. So this is A and has some characteristic length L is given by this form. So just invoking CFT, you have some ability to quantify the entanglement entropy so long as it's geometric. It's somewhat limited. For example, even in 1+1 dimensional CFT, the entanglement entropy of 3 disjoint regions is not known when they're close to each other. So this gives you a hint that CFT allows you to go further. And then in ADS CFT, we have the Ryutaki-Yanagi formula, which geometrizes the entanglement entropy. So S of rho A is equal to the area in the bulk subtending A over 4G, drawing the picture that everyone has. This is A. This area, the area of this minimal surface. The area of this minimal surface in the bulk calculates the entanglement entropy of the boundary region A. It's not flat because of the curvature of ADS space. I'm sorry for being pedantic, but I just want to make sure that everyone's at the same level before I go further.
Quick question, Ning. You
Yeah.
mentioned that entanglement entropy of 3 regions when they approach each other is not known. Is it expected to be universal?
Yeah, I don't see any reason why it shouldn't be.
You think it's universal?
I do.
Oh, okay.
Is there a reason why you think it shouldn't be?
Shouldn't it involve 3-point functions?
I don't, so my answer for that is that there's a universal holographic answer. And you could have said the same thing there. So like, take any holographic 2D CFT. We believe the Ryutaki-Yanagi formula is correct for all of them. And so in particular, I'm allowed to take my boundary regions that are homologous to that my RT surface is homologous to be arbitrarily close to each other. And nevertheless, the form there is universal. So I have this intuition that in 1+1 CFT in particular, 1+1 CFTs are closer to holographic CFTs, even at low central charge, than in higher dimensions, so long as we ignore back reaction and dynamics. And if we're calculating entanglement entropy on a static time slice, like with Ryutaki-Yanagi, then we're exactly in that region. So that's why I believe that it's true, but it certainly hasn't been proven.
But if I have 3 regions and I bring them closer, it's like a one big region. There's 2 per region.
Yeah, so you'll get
Yeah.
increasingly important UV corrections as you take 2 regions that are far away from each other and you bring them close to each other, this middle one, if I use RT like intuition, is going to be increasingly the non-divergent piece of it will become smaller and smaller until eventually it completely goes away once the two regions become adjacent.
Alright, we don't have to talk about this, but I was under the impression they should involve 6-point functional twist operators.
Yeah, I mean, so I can imagine those entering as subleading corrections. So maybe they only matter at subleading order.
Sure, okay, sure.
So what does this do? The RT formula geometrizes the entanglement entropy. And so it turns this difficult nonlinear linear algebraic question that we needed to do to try to construct bounds for the entanglement entropy into a geometric question. So I'll quickly do the parlor trick that everyone that does a holographic entanglement entropy calculation talk does. And I'll just prove SSA holographically. So the minimal surface calculating S of AB is this one. Calculating S of BC is this one. Calculating S of B is this dashed one. And S of ABC is this outer dashed one. So if I cut and reglue and I associate this portion and this portion with the outer one, clearly at non-minimally, it's homologous to ABC, but it's not necessarily minimal. And if I take these inside ones, which I mark with an X, and I associate it with the one that's the minimal surface with B, clearly those pieces non-minimally subtend B. And so by recombining them here, it's easy to see that SAB plus SBC is greater than or equal to SB plus SABC. There's some case analyses that you need to do when A, B, or C are made up of multiple disjoint regions, or if they're not exactly adjacent to each other, but it's a simple enough case analysis that it doesn't dramatically make the situation more complicated. Okay, so however, this comes at a cost. Not all entanglement entropy inequalities for states that obey RT are obeyed by all quantum states. In other words, there exist entanglement entropy inequalities for holographic states that are dual to semi-classical bulk spacetimes that are not obeyed by all quantum states. And indeed, the first novel one that you can find for that's true for all holographic states that you can prove in a very analogous style, how this was proven, is this MMI inequality. And notably, this is violated by GHZ states, so states that look like this. Because when you have a GHZ state, all of these entropies are the same, you can easily show. And so this would imply that 3 is greater than or equal to 4, which is not true. So is this a bug or is this a feature? I would like to argue that you can think of this as a feature, because this means that entropic properties of quantum states give necessary conditions for holography. And this is in contrast to HPPS. What I mean by that is that there are two different ways of thinking about necessary conditions for holography. You can take HPPS, which are conditions on the theory. So they tell you that the theory needs to have a sufficiently large central charge and a sufficiently sparse low energy spectrum. But these are also necessary conditions, but they're agnostic of the theory. They only care about properties that can completely be derived just given the state without knowing the Hamiltonian at all, or the Lagrangian at all. And these tell you that in order for those bulk regions to obey Ryu-Takeyanagi, so in some sense, in order for the bulk regions to be geometric, certain entropic properties need to be obeyed by those states. So it's an independent set of conditions that are necessary for allowing a particular state in a particular theory to be holographic. Clearly these are not sufficient by themselves, because I could find something that obeys all of these inequalities that, for example, is a state defined in a very small central charge CFT. And so it would fail the necessary conditions for the theory. But they're just independent necessary conditions. Okay. So what I did.
Sorry, Ning, maybe you'll say this later, but are we gonna specify what subset of these holographic inequalities apply in 2D CFTs as well?
No, that wasn't part of my plan.
Is there an understanding of it though?
My intuition should be that they should all apply. For ground states and thermal states in 2D CFTs, but I haven't proven.
So then, but based on your intuition, you would say that these inequalities are necessary but insufficient for holography.
Yes, but it's
Okay.
possible that if you combine these conditions with HPPS, then together they would be both necessary and sufficient.
That's right. So HPPS claimed that they are necessary and sufficient.
Well, I mean, it's kind of clearly not true, because I can take an arbitrary state, like a random state in HPPS, in a CFT that obeys the HPPS conditions, and that state is clearly not dual to a classical bulk space-time. Like just,
Well, let's continue this. Okay, yeah, sure.
Sorry, I
Yeah.
have a side question.
Yeah.
So MMI is violated by GHC4, but
Mhm.
GHC3 saturates MMI, right? So
Yeah, I think so.
Sorry,
Yes.
do you know if there are any other holographic inequalities are violated by GHC3?
Any other holographic inequalities that are violated by GHC3? I don't think so, because for all intents and purposes, GHC3 has the same entanglement spectrum as 3 bell pairs. And so 3 bell pairs is kind of dual to like a 3-sided wormhole. Like it's like a Planck scale version of a 3-sided wormhole. So I don't expect there to be any holographic inequalities that violate GHC3.
I see.
It's too simple, and it's kind of like a degenerate case. That's why you don't see it. That's why you need to go to higher partite, multi-partite states to really see it. Because at the entropic level, you're insensitive to the difference between one copy of GHC3 and 3 bell pairs.
I see.
Okay.
Thanks.
Okay, so in this work, we defined something called the holographic entropy cone from 8 years ago now. And so this object is the cone, it's a cone whose surfaces are true inequalities for all holographic states. And moreover, any entropy vector outside the cone is non-holographic, which you can just think of this as this being a tight cone for holographic states. Yeah, so it's trying to define what portion of the entropy space can be consistent with holography. So that's what motivated us to define this object. And what we end up finding is that this geometrization of entanglement entropy it can be automated into a contraction map condition. So the best way to explain the contraction map is via example. So let's take MMI as an example. The left-hand side had an AB, a BC, and an AC, and the right-hand side had an A, B, C, and an ABC. So the terms that appear in the left and the right-hand side define the dimensions of a hypercube. So because there are 3 terms on the left-hand side, it's a 3-dimensional hypercube or just a normal cube. Where what I care about, the vertices are given by from 0, 0, 0 to 1, 1, 1. So something that's 0, 0, 0 would correspond to a bulk region that is outside the AB RT surface, outside the BC RT surface, and outside the AC RT surface. And something that's all ones would correspond to something that's included in all 3 RT surfaces at the same time. And it's not hard to convince yourself that every bulk region can be classified by one of these binary bit strings. Because they're either up to a set of measure 0 that lie exactly on the RT surfaces where there's some small ambiguity. Everything's going to be inside or outside of any of these surfaces. So I can take the bulk, construct a graph, a discretization of it that is complete. Okay. So then the left-hand side bit string, the left-hand side hypercube are these. The right-hand side one, in order to find the contraction map, we need to figure out how the vertices on the left-hand side hypercube map into the right-hand side hypercube. So the contraction condition is simply that the Hamming distance between any 2 vertices x and y on the left-hand side hypercube need to be greater than or equal to the Hamming distance between their images on the right-hand side hypercube. Now, this condition is extremely easy to satisfy if you don't have additional constraints, because I can simply map all of the vertices on the left-hand side hypercube to the same vertex on the right-hand side hypercube. The right-hand side Hamming distance would always be 0, so this condition is trivially satisfied. Or I can map, if the right-hand side hypercube is bigger than the left-hand side hypercube in terms of number of vertices, I can just embed the left-hand side hypercube into a sub-hypercube of the right-hand side hypercube. And then that would preserve all the Hamming distances, so it would also saturate this condition. Clearly, I'm not interested in these trivial examples. So what is the extra data that we need? Well, the extra data are these so-called initial conditions. So we have a system called O, which is just everything that's not A, B, or C. And it needs to be excluded by all 3 of these. But it also needs to map onto a right-hand side bit string where it's also excluded by all of those. And then if we have the single character region C, then it needs to be excluded by AB, included by BC, and included by AC. And on this side, it needs to be excluded by A and B, but included by C and ABC. And similarly, I think this one is B, so it's 0, 1, 0, 1. And this one is A, so it's 1, 0, 0, 1. So the part that makes the constraint non-trivial is that these single character things, their left-hand side to right-hand side bit string maps are fixed. And the question is, given this constraint or initial condition, can we still find a contraction map that satisfies this property? And if you can, then your holographic entanglement entropy inequality is true. So this is the main theorem from the holographic entropy cone paper. So we can construct this geometric thing into this contraction map method and thus computerize it. Now, what we did back then is we just did a brute force search for contraction maps in this way. So if someone gives us a candidate inequality, we try the possible 0, 1 bit string assignments on the right-hand side from these things. And then we stop when we find one that satisfies all of the contraction condition. So that takes an exponential amount of time, right? Because it's a brute force search. this thing is exponential in the number of entries, and we need to try 0 or 1 for all of them. So it's clearly not very efficient.
Ning, is there a graph theory way of describing all of this? It seems like there is something very graph theoretic about this.
Yeah, there definitely is. I can talk about that next. So along the way, holographic entanglement entropy, we also found the following thing. All inequalities concerning cut functions, min-cut functions on any graph obey the same inequalities as the holographic entanglement entropy. And this is kind of an automatic corollary because on the way to constructing the holographic entanglement entropy, we discretized the bulk into graphs, and then we proved a theorem that was true for any graph. So in some sense, the graph theory theorem is the main theorem, and the holographic entanglement entropy result is the corollary. But if you're a physicist, you can think about it this other way. And this is, as an aside, this is somewhat interesting because graph cut functions are submodular, where submodular is just the graph theorist's way of saying that they obey SSA. They're formally exactly the same. Moreover, graph theorists know that not every cut function, sorry, not every submodular function is representable by graph cuts. And they have counter examples as to why, but as far as I can tell in their literature, they don't know the reason why. And the reason why we found accidentally, it's because of this. It's because the reason why not every submodular function can be represented by graph cuts is because there are additional inequalities that all graph cuts must obey. And we kind of accidentally found them on the way to proving something for holographic entanglement entropy. And the reason why this is maybe interesting if you're not a physicist is submodular functions and submodularity is very important in convex optimization. If you're trying to do convex optimization for a submodular function, there are special tricks that you can do that dramatically speed up your ability to do those optimizations. And so I think it's a very natural question to ask, if you use some of these additional constraints that those graph cut functions have to obey, does it yet further dramatically speed up convex optimization problems that must obey those properties? But that's an aside. So all of this is an aside. Okay, so are there any questions to this point about what I've described so far? Because I'm going to start talking about things that depend on a clear understanding of what I've already said, starting from it.
I have a question. So the min cut connection, the connection to min cut and graph theory makes it sound like these inequalities are explored on a constant time slice in the bulk. Is it just like simpler to explain in that case, or do you think that, or is it the limit to which we understand these inequalities, or?
So good. So in 2015, when we proved these inequalities and subsequent inequalities that were proven, they are true on constant time slices. We know that that's correct. There has been an ongoing effort by Hedrick, Hubani, Grado White, and one of Matt's students, I think Guglielmo, I forget his last name, but in order to prove that these entropy inequalities that are also covariant, they're also true for HRT. And my understanding is that they strongly believe that it's true, but there's a few like holes in their proof that they haven't been able to plug. But their proof strategy is also taking the covariant entropy regions and constructing a graph dual of them. Because the idea is that once you find a graph dual, all of the techniques go through automatically.
I see.
And they can in general, but there's like a few annoying cases which they don't know how to deal with.
I see. Thank you.
Okay, any other questions from younger people? I want to make sure that like I haven't lost people that don't work on this. Haven't worked on this for like a decade. If you have questions, speak up, because I would rather you get something out of the talk than not get something out of the talk. Okay, so what did I just say? Contraction maps. The original work, they were found by brute force. 0, 1 assignments to every RHS bit. Very slow, computationally intensive. We already have a problem that we suffer from a combinatorial explosion. Like with many problems in discrete math, graph theory, of combinatorics, there's something called a combinatorial explosion, where when you're trying to prove these things for n equals 5, it's easy, and for n equals 6, it's impossible. Because like the number of options explode combinatorically. So that means that there was a need, if you find these inequalities interesting, which you don't have to speed up the contraction. That was the focus of our work. We wanted to understand how to speed up the contraction map from this exponentially slow thing to something that was runnable. And so in order to do that, let me rewrite the MMI table, which I didn't complete notably last time. And let me show you how a person would complete it. And O A B C, this is 0, 0, 0, 0, 0, 0, 0. And this is 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1. Sorry, this is A, C, D. This is 0, 1, 1, 0, 0, 1, 1. And then we need to map every vertex on the left-hand side to a vertex on the right-hand side. So let's say we're interested in trying to figure out how this vertex needs to map, right? We know that this vertex is Hamming distance 1 from the all zeros bit string. So we know that it needs to be this one from the all zeros bit string on the right-hand side. But if we compare it with A, we know that it's also distance 1 from the 101 bit string. So it also needs to be distance 1 from 1001, right? So that immediately means that, well, these two are already distance 2 from each other. So that means that this bit string must map to a thing which inherits the matched bits from these two. Because if I change one of these two, no matter what assignment I make to the other one, it'll be distance at least 2 from at least one of these things. And we know that it has to be distance at most 1 for it to be a valid contraction map, right? However, if we take a look at this thing and we compare it with the C bit string, it's also distance 1 from the C bit string. So we also know that it's distance 1 from 0, 0, 1, 1. Okay. So that means that it needs, again, to fix the match bits there. So that means that that one has to be a 0. And by similar analysis, you'll be able to see that this one is a 1. And by going through that analysis, you can actually deterministically and fully fix the rest of this contraction map just following that rule. So what did we actually do? What we actually did is we intuitively defined something called a Hamming distance preserving path. So a Hamming distance preserving path is defined by two vertices x and y such that the Hamming distance between x and y is equal to the Hamming distance between f of x and f of y. Right? And moreover, it means that all vertices on a Hamming preserving path between x and y must, so I guess I'll label this all vertices w on a Hamming preserving path x and y must map to f of w that inherits all matched bits between f of x and f of y. In other words, whenever I have a Hamming preserving path, the geometric way of thinking about it is I have a sub-hypercube of the left hypercube that's matched onto an isomorphic sub-hypercube of the right hypercube. And so when that happens, that means that all vertices in this sub-hypercube on the left must map to vertices on the sub-hypercube to the right. And the definition of what it means to be a sub-hypercube of a larger hypercube is that the other bits that are not free to vary must all be fixed. And so that's how you get this condition.
Yeah, can I ask you a question, Ning? So each of these binary codes, they represent a region in the bulk, right? That's
Okay.
so the Hamming distance between two codes is it the minimum number of RT surfaces that any path that connects the two will have to necessarily cut?
Yes.
Okay, so that is a Hamming distance.
Modulo degeneracy, right?
Did you see?
So you can have situations where multiple of the RT surfaces lie on top of each other. So for
Yeah, sure. Well, let's say they don't, yeah, correct. Let's say they don't overlap, so it's really the minimum number of RT surfaces that you have to cut to get from one region to another one. Now,
Mhm.
okay, now with that, I wanna think about what you just said. So now a Hamming distance preserving map becomes a map that does not change that?
Yeah, so it tells you that there's a certain rigidity to the cutting and regluing procedure. That certain cut and reglue, that certain sub aspects of the cut and regluing procedure are rigid and inflexible.
I see.
Sorry, is there any way to see that there always exists such a function which does not increase the Hamming distance for all mappings?
No, that definitely is not true. So if someone gives you, if you try to construct a contraction map that corresponds to a false entanglement entropy inequality, it will precisely fail to have the contraction. That's in some sense what makes it useful, because if you find a valid contraction map, you know the entropy inequality is true, modulo these caveats that Nima's pointed out on constant time slices and probably on HRT, but not proving.
So these partitions of regions, we don't know a priori because we don't know the inequality.
Right. So there's no there's no analytic way of eyeballing an inequality and knowing immediately what the contraction is. It would be nice if there was, but it would make my life a lot easier, but it doesn't exist. Okay, so this.
Sorry, Just one quick question. Is just naively, are there any connections between these Hamming distance preserving maps and isometries of the graph? Or is it just like misguided?
I mean, in some sense, they're precise sub-isomorphisms of the graph. So it
there are
tells you,
special isomorphisms of the graph, is that right?
yeah, so they specifically map a sub-hypercube of the left-hand side of fixed dimension to a sub-hypercube on the right-hand side of the same fixed dimension. So that's a very special isomorphism.
Thank you.
Question, Ning,
You're not allowed to ask questions. Fine. You're
Oh.
go.
So if we know this F, which is, I think you are calling path.
Mhm.
Path. How is this different from contraction map? In the contraction map, you have an inequality, and here it saturates the inequality.
Yeah, so the idea
path.
is that so the idea is that some if I have a valid contraction map, there exists some subset of vertices on the left-hand side that will fulfill this Hamming preserving path property. Not all of them will. So remember that the general contraction condition is that the distance between x and y is greater than or equal to the distance between f of x and f of y. So this is stricter, right? This is saying that there exists x and y. So this is a statement for all x, y. And here it's like there exists x, y. And this is the difference. Well, this and this is the difference. Does that make sense?
Yes.
So the idea is, can we use these rigidities to very efficiently fix some large portion of the mappings from the left-hand side contraction map to the right-hand side contraction map? Because at the end of the day, the key concept that I'm sneaking into this ADS CFT inspired talk is an algorithmic one, right? I'm trying to find a speed up in the contraction map algorithm. So once I think about it that way, I don't need to think about physics anymore. It's just a mapping from bit strings to bit string. So I can think about it as a mathematician or as a computer scientist. So there's a second condition, which I guess I'll write down here, where if the distance between x and y is already equal to the distance between the fixed bits between f of x and f of y. In other words, if f of x is 0, 0, question mark, and we don't know what they are, and if f of y is, say, 1, 1, 0, 0, so something exactly fixed, and we know that the distance between x and y is equal to 2. So just in the fixed that are fully in the bits that are fully fixed on the right-hand side, the distance is already equal to 2. So that means that we know that these two bits must be 0, 0. Because if they were anything else, they would increase the Hamming distance on the right-hand side. So if this is true, then unfixed bits must match. This is the second condition. And then there's a third, more complicated condition involving if a vertex is on 2 or more Hamming preserving paths at the same time, then something more complicated happens, but it's like the same flavor of thing that we're doing here. These are the only 3 routines. We'll call them method 1, method 2, and method 3 that we will use in order to find a faster contraction. So you can
Sorry, you defined Hamming preserving maps. What is a Hamming preserving path?
I defined Hamming preserving paths. So a Hamming preserving path between 2 vertices x and y on the left-hand side is said to exist if the distance between x and y is equal to the distance between f of x and f of y.
Oh, okay. Okay, good. All right.
It's kind of a misnomer to call it a path, because that means actually that every minimal path between x and y is a Hamming preserving path. So if you like, you can think of it more precisely as a Hamming preserving isomorphism between the subhypercubes that they define.
Yeah.
But you can also think about the specific if you like. Okay, so the punchline is that if we use these 3 methods and we use them iteratively, it gives an exponential speedup. of contraction maps to a polynomial time algorithm. So compared to the brute force thing, instead of something that takes an exponential amount of time, we now have something that takes a polynomial amount of time. And to give you a sense of how much faster it is. So Sergio, Veronica, and Frederick Jia found like a few hundred inequalities. And it took Sergio using the contraction map method, something like several months to a year running on a cluster to prove these inequalities. We proved all of these inequalities once they gave us the list in 2 weeks. So it's much faster. And this was like, I think Joydeep is in the call. This was like while Joydeep was writing the code from scratch. So certainly the first few instances that we ran were not optimized. So it really is much faster, both in principle and in practice. And one of the things that we've done now is that Sergio has also come up with like about the order of 1,000 new inequality candidates. Ways that he gave to us. No one has managed to prove these, and I think Joydeep proved like 800 or 900 of them in like 1 week or something. All of these, I guess, were too tedious to prove using the original method. So it's not just that it's in principle better. Like you can have a polynomial algorithm where the pre-coefficient could be like 10 trillion and then it's not actually better. It's actually in practice better. So good.
Sorry,
So
just one question. Is there any understanding of how the number of inequalities grows with the number of partites, number of subsystems?
yeah. So if you think about the inequalities, whether an inequality is included or not as like a random thing, then typically the number of terms that appear on the left-hand side or the right-hand side grow exponentially with the party number. So like inequalities tend to include most, if not all, of the possible terms that are allowed. And the number of distinct terms that are allowed for a 5-party thing is like 2 to the 5, right? It goes from like the trivial entropy to S of A, B, C, D, E. And for every thing A, B, C, D, or E could be either included or excluded. So then typically you get something that's of order 2 to the n terms on the left and of order 2 to the n terms on the right, divided by 2 roughly, because if it appears on one side, it won't appear on the other side. And so the number of terms increases exponentially, but the number of terms is what defines the dimension of the hypercube. So then the number of contraction map conditions that you need to satisfy will also then grow exponentially with the number of parts.
So then you're saying that the intuition is that the number of states that satisfy all these inequalities is a Pauli subset of the exponential number of states in the Hilbert space.
Yes. Which makes sense because we know that holographic states are relatively rare in the set of all quantum states. So this means that even observing a coarse property like just their entropic properties, you can already see this.
Thank you.
Yep. Okay, so some other things that we did, completeness. So you might want to know that if a contraction map does not exist, then that means that the inequality is false. So this wasn't shown before, and we show it. So now we know that if you fail to find a contraction map, you can construct a counterexample that corresponds to your failure to construct the contraction map, which corresponds to a bulk space-time geometry that violates that inequality, which is nice. Another thing that I'm interested in is generating novel contraction maps. So there's a pure math problem that you can phrase here, where you take as input two integers, m and n, where these two just define the dimension of the hypercubes that you're trying to find a map between. And your goal is to find all contraction maps. Between a hypercube of dimension m to a hypercube of dimension n. So because we know that it's complete, and because we know that every time a contraction map exists, it corresponds to a valid inequality. If you can find some systematic classification in functional analysis of all contraction maps of this form, you'll have provably found every possible holographic inequality. And they'll all be true. Many of them won't be tight, right? So for example, if I talk about the trivial examples that I mentioned before, where I take the full hypercube here and I map them to a single point, it's not hard to convince yourself that this corresponds to the inequality that the sum of a set of entropies is greater than or equal to 0. And if I do an isomorphic map from a hypercube of dimension m to the exact same hypercube of dimension m, so I just map every vertex to its corresponding vertex in a one-to-one way, then this corresponds to the inequality the sum over I s of ai is greater than or equal to the sum of I of s of ai. So it's tautologically true. And so these are uninteresting. But if I can find a complete classification, then I will by construction have found all of the interesting ones. As far as I can tell, this is a very hard math problem. It's very difficult for non-trivial M and N to find all possible contraction mappings of this style. So one of the things that I'm starting to work on is to use machine learning, in particular genetic algorithms, where I start with valid contraction maps from the entanglement entropy inequalities I already know for a fixed M and N. And then I introduce mutations, single vertex map mutations, where I take the mapping of a specific vertex x that previously went to f of x, and I now map it to f prime of x, which maybe is distance 1 from f of x. And then once I do that, I check goodness of fit. So I should go this way. Which just is the same as, does this new map also satisfy the contraction condition? And then this feels to me like a thing that's very naturally implemented in genetic algorithms, where you literally take some large population, you introduce small mutations, and you see if the new mutations continue to succeed. And so in this way, this will not find in general all of them. But my question is whether these ML-inspired technique can find novel inequalities that the other ones can't, that maybe then can inspire the search for new infinite families of inequality. Something else that I wanted to say. No, I think at this point I'm happy to take questions.
Thank you so much. Are there any questions? We had plenty of questions. So are there more questions?
I have one question, so. And then you were trying to find like all the maps, contraction maps. But if I go back to the earlier like thing where you wanted to see whether inequality is true or not, and you were finding a contraction map, finding whether it happens. Do you think finding that it doesn't exist there might be a faster algorithm to say it doesn't exist rather than like trying to find it?
Well,
We don't care what the map is, right? We just care whether it exists or not.
yeah, so the secret that I didn't mention is that there are two computerized things that you need to do. when you're trying to find a new inequality. The talk that I gave was largely focused on if someone gives you a candidate inequality, trying to verify whether or not it's correct. But then there's also the other piece, which is generating candidate inequalities.
Right.
And so the reason why this finding a contraction map way is kind of elegant is because it does both at the same time. If you find a contraction map, then you can read off what the inequality corresponding to it is, and it's by construction true. Now, it's worth pointing out that in this way of thinking about things, it completely obfuscates the initial constraints. And that's because whether or not a contraction map that obeys like the contraction condition is independent of the existence of these initial conditions. That's why we can land on these trivial ones where previously we couldn't. And the idea is that once you find many or all of these contraction maps, then you can retroactively restore what the initial conditions are. And once you've restored what the initial conditions are, that allows you to read off the entanglement entropies based on whether each column includes or excludes every possible single character. That lets you write down what the column labels are, and that will correspond to a true inequality. Does that make sense?
Yeah.
Cool. Any other questions?
I think there's something basic I missed. Can you go back to this diagram you drew for MMI, ABC? Yeah, this one. So if it's like a four-partite system, how does the diagram change? I'm kind of confused. So the tripartite systems would still be on the right?
No. So, okay. So maybe I wasn't clear enough with this. So
I think, sorry.
generically, your inequality will be some sum of S of AI is greater than or equal to some sum of S of AJ. Right? This
Yeah.
is with positive coefficients or with unit coefficients if you allow repetition. Then all I'm saying is the column labels here go from A1. Sorry, I'll make this S of BJ. This will be A1, A2, AI. So the terms that appear on the left-hand side define the columns and therefore the dimension of the hypercube. And the terms that appear on the right-hand side will define the columns that appear on the right-hand side.
Oh, sorry. So the left and right are decided by the fact that the coefficient in this inequality is it positive or negative?
Mm-hmm.
Oh, I see. Okay, thank you. Because I think the MMI example confused me. All right, thank you.
Yeah, I mean the MMI confused Patrick, Alex, and Matt too, right? Because that's why they picked the wrong generalization to try to prove.
Yeah.
And that one wasn't true. Basically, like they got the only reason why we wrote a paper that they didn't write several years earlier is because S4 and D8 are the same group. And so they decided to look at SN, whereas the thing that they should have looked at is B2.
Okay, thank you so much, Ning.
Yeah.
And,
If you guys have any other
yeah.
questions,
Any last questions? If not, let's thank Ning again. Thank you so much, Ning.
Yep. Thanks, guys. Bye.
All right, bye.